Good morning to one and all. This is Dr. Padma, Assistant Professor, Department of Physics, Institute of Aeronautical Engineering. Today's topic is Transferred Electronic Device. Transferred Electronic Devices called as simply TEDs. So, topics are introduction of the transferred electron devices, gun effect devices or gun diode, domain formation of gun diode, construction of gun diode, and typical characteristics of the gun diode, applications of the gun diode. These are the topics are going to be covered in this session. Transferred electronic devices. So the common characteristics of all active two-terminal solid-state devices is their negative resistance. So negative resistance is the common characteristics for all the active two-terminal solid-state devices. So the real part of their impedance is negative over a range of frequencies. So the real part of their impedance is negative over a range of frequencies. So in a positive resistance, the current through the resistance and the voltage across it are in phase. So in positive resistance, the current through the resistance and voltage across. So the current and voltage are in phase. So the voltage drop across the positive resistance is positive, and a power of I square R is the power. So the power of I square R is dissipated in the resistors. So the common characteristics of the all active two-terminal solid-state devices is their negative resistance. So negative resistance is the common characteristics of all the two-terminal solid-state devices. So the real part of their impedance is negative. So those are having negative impedance over a range of frequencies. So in a positive resistance, if you take a positive resistance, the current through the resistance and the voltage across it are in phase. So the current and voltage both are in phase. So in positive resistance, the current and voltage both are in phase. So the voltage drop across the positive resistance is positive. So the voltage drop across positive resistance is positive. And the power of I square R is dissipated in the resistor. If in negative resistance, the current and voltage are out of phase. So, for example, if you take a positive resistance, means the current and voltage are in phase. If you take a negative resistance, the current and voltage are out of phase. Those are out of phase by 180 degrees. Those are out of phase by 180 degrees. So the voltage drop across it is negative, and a power of minus I square R is generated by the power supply associated with the negative resistance. So in a negative resistance, the current and voltage are out of phase by 180 degrees. So the voltage drop across it is negative. For example, if you take a positive resistance, means the current and voltage are in phase and the voltage drop across it is a positive. So in a negative resistance, the current and voltage both are out of phase by 180 degrees. Current and voltage are out of phase by 180 degrees. So the voltage drop across it is negative, and a power of minus I square R is generated by the power supply associated with the negative resistance. So in other words, positive resistance absorb power. So the positive resistances absorb the power. Those are called passive devices, and negative resistance or generates the power. Those are called as the active devices. So the positive resistance absorb power. Those are called as the passive devices, and the negative resistance which generates the power. Those are called as the active devices. So TEDs, transferred electronic devices, are bulk devices having no junction or gates as compared to microwave transistors. So we are compared with the microwave transistors. TEDs are bulk devices having no junction or gate as compared to microwave transistors, which operate with either junctions or gates. So the positive resistance absorb the power are called as the power passive devices, and negative resistance generate the power called as the active devices. So transferred electronic devices all are the bulk devices having no junctions or gate as compared to the microwave transistors, which operate with either junctions or gates. TEDs are fabricated. Transfer electronic devices are fabricated from compound semiconductors. Those are gallium arsenide, indium phosphide, cadmium telluride as against germanium and silicon. So, for over the germanium and instead of germanium and silicon, we are using gallium arsenide and indium phosphide and cadmium telluride for the fabrication of the transferred electronic devices. So, transferred electronic devices are fabricated from the compound semiconductors such as gallium arsenide, indium phosphide, and cadmium telluride over the germanium and silicon of the transistors. So, transferred electronic devices operate with the hot electrons whose energy is very much greater than the thermal energy. So, compared to thermal energy, hot electrons are having very much greater energy compared to the thermal energy. So, transferred electronic devices are operated with the hot electrons whose energy is very much greater than the thermal energy. So, whereas transistors operate with warm electrons. So, transistors are operated with warm electrons whose energy is not much greater than the thermal energy, that is 0.026 electron volts at room temperature. So, gun diode is an example of the transferred electronic devices. So, transferred electronic devices are fabricated with compound semiconductors such as gallium arsenide, indium phosphide, and cadmium telluride as against the germanium and silicon of transistors. So, transferred electronic devices are operated with the hot electrons whose energy is very much greater than the thermal energy. So, whereas transistors are operated with the warm electrons whose energy is not much greater than their thermal energy, that is 0.026 electron volts at room temperatures. So, gun diode is an example of the transferred electronic devices. Then coming to the gun effect devices. Gun effect devices means gun diode. So, the gun effect diodes are named after J.B. Gunn. So, the gun diode is discovered by J.B. Gunn in 1963, who discovered periodic fluctuations of current passing through the N-type gallium arsenide specimen. So, he has taken the N-type gallium arsenide specimen. He observed that the periodic fluctuations of current passing through the N-type gallium arsenide specimen when the applied voltage exceeded a certain critical value, that is 2 to 4 kilovolts per EMS. So, gun effect diodes are named after J.B. Gunn, who discovered the periodic fluctuations of the current passing through the N-type gallium arsenide specimen when the applied voltage exceeds a certain critical value 2 to 4 kilovolts. So, gun effect can be explained on the basis of the two-valley theory. So, two-valley theory of Ridley-Watkins-Hill sum, that is called RWH theory, or the transferred electronic mechanisms. So, the gun effect can be explained on the basis of the two-valley theory. Two-valley theory means lower valley and upper valley, that is called L valley and U valley. So, gun effect can be explained on the basis of the two-valley theory of Ridley-Watkins-Hill sum, RWH theory, or the which is also called as the transferred electronic mechanism. So, transferred electron mechanisms. So, the basic mechanism involved in the operation of the bulk N-type gallium arsenide devices is the transfer of electrons from lower conduction valley, that is called L valley, to the upper subsidiary valley, that is called U valley. So, the basic mechanism inside the gun diodes or N-type gallium arsenide devices is the transfer of electrons from, this is L valley. So, the transfer of electrons from L valley to U valley. U valley is called upper valley. So, the basic mechanism is involved. The basic mechanism involved in the operation of the bulk N-type gallium arsenide devices is the transfer of electrons from the lower conduction valley, that is called L valley, to the upper subsidiary valley, that is called U valley. The transfer of electrons from the L valley to U valley, that is the mechanism involved in the operation of the gun diodes. As shown in the figure, the curvature of the two valleys in the conduction band are also called as the the two curvatures. The two curvatures of the conduction band is also called as the subbands. Those are different, so that an electron L value has a smaller effective mass. So the electron in the L value has a effective mass m1 equal to 0.072 m naught. M naught is the mass of the electron. So the electron in the U value mass is m2 equal to 1.2 m naught. So as shown by as can be observed from the figure, so the curvature of the two values L value and U value in the conduction band are also called as the subbands. Those are different, so that the electron in the L value has a smaller effective mass. The smaller effective mass m1 equal to 0.072 m naught. That is smaller than the electron mass in the U value. The electron in the U value effective mass is m2 equal to 1.2 m naught, where m naught is the effective mass of the electron. So from the figure we observed that here m1 equal to 0.072 in L value, the effective mass of the electron is 0.072 m naught, and mobility mu1 equal to 0.5 meter square per volt second. So whereas the electron in the upper value, the effective mass is 1.2 m naught and the mobility is 0.01 meter square per volt second. The energy gap is 1.43 electron volts. This is the conduction band, this is the valence band. This is the gallium arsenide energy bands. This is the empty energy band, narrow forbidden gap, and filled energy band. So this one is the partially filled energy band. The different effective masses means different mobilities. So the effective masses are different for U value and L value. So the mobilities are also different. The mobility value for L value is mu equal to 0.5 meter square per volt second, and the mobility for U value is mu2 equal to, this is mu1 mu2 equal to 0.01 meter square per volt second respectively. So the different effective masses means those are having different mobilities for the L value. The mobility for L value mu1 equal to 0.5 meter square per volt second, and the mobility for U value is mu2 equal to 0.01 meter square per volt second respectively. So the ratio of density of states in the U value to that L value is about 60. So if you take the ratio of the density states for U value and L value, the ratio, if you take the ratio of the density states in the U value to the L value is about 60. Thus the upper valley has a very high density of states compared with the k equal to 0 locations. So if you take k equal to 0 locations, the upper valley has a very high density of states compared with the lower valley. So the ratio of the density of states in the U valley to the L valley is about 60. So the upper valley has a very high density of states compared with the lower value when k equal to 0 location. At low or zero electric fields, if you take low or zero electric field, conduction electrons are distributed in a manner determined by the energy separation. Here, dou E is the energy separation. So the lattice temperature T naught and the density of states. So with the typical value stated in the figure, most of the electrons at lower electric fields and at low temperatures will occupy states in the L valley and carry ohmic current J equal to sigma A, where J is the current density sigma J equal to sigma E. So at low or zero electric fields, the conduction electrons are distributed in a manner that is determined by the energy separation dou E. The dou E is the energy separation. So the lattice temperature T naught and the density of states. So with the typical value stated in the figure, most of the electrons at low electric fields. So many of the electrons at lower electric fields and low temperatures will occupy the states in the L valley and carry the ohmic current is J equal to sigma E. So at lowest electric fields and low temperatures. So low electric field and low temperatures. So most of the electrons are occupied the states in the L value. at the low electric fields and low temperatures, most of the electrons occupy the states in the L value and carry the ohmic current J equal to sigma E. With sigma is similar to P N1 mu1, that is similar to E N0 mu1, where N1 is the carrier concentration in L value and is assumed to be equal to the total carrier concentration N0, and mu1 is the mobility in the L value. So with the sigma is similar to P N1 and mu1, where N1 is the carrier concentration in the L value. So which is equal to the total carrier concentration, that is N0. Total carrier concentration is N0 and mu1 is the mobility in the L value. So as the applied field is increased, so the electrons gain energy from it and move upward in the U value. So if you if we increase the applied fields, then the electrons gain the energy from it. So for example, at lower electric fields, most of the electrons are occupied the states in the lower value. So at low electric field, most of the electrons occupy the states in the lower value. So if you apply the electric field is increased, then the electrons are gain the energy from that applied electric field and take a transition in the upward direction. So those are moving from lower value to upper value. So L value to U value. So actually the probability of this inter-value transfer of electron is good, as there are many available states in the U value. So as the applied field is increased, so the electrons are gaining the energy from the electric field and moves upward in the U value. So the probability of this inter-value transfer of electrons is good, as there are many available states in the U value. So as the electrons transferred to this U value, their mobility decreases. So after the transition of the electrons from lower value to upper value, their mobility will be decreased and the effective mass is increased. Once the mobility decreases, means effective mass will be increased, thus the decreasing the current density J and hence the negative differential conductivity. So at the upper value, the conductivity is negative. So the transfer of electrons, as the electrons transfer to this U value, means their mobility decreases and the effective mass is increased. Thus, that means the decreasing the current density J and hence the negative differential conductivity. So once the electron is transferred from lower value to upper value, means the mobility will be decreased. Once the mobility decreases, means it increases the effective mass and which decreases the current density J and hence the negative differential conductivity obtained. There is a certain threshold, approximately 3.3 kilovolt per centimeter, above which this intervalley transfer, also known as the population inversion. So there is a certain threshold. So if you fix a certain threshold, approximately the threshold value is approximately 3.3 kilovolt per centimeter, above which this intervalley transfer means the transition of the electrons from the lower value to upper value, which is also called as the population inversion of charges from lower value L value to the upper value, or the transfer of electron effect takes place. So as the transfer of electron is taking place, the current density should be given as so there is a certain threshold, approximately 3.3 kilovolt per centimeter, above which this intervalley transfer of electrons from lower value to upper value, which is also known as the population inversion, or the transfer of electron effect takes place. So as the transfer of electron is taking place, the current density should be given is J equal to sigma A, that equal to rho into N1 plus N2 mu bar into E, that equal to E N0 mu bar into E. So where mu bar is the mobility equal to N1 mu1 plus N2 mu2 by N0. So that is the average mobility of the electrons. So where mu bar is the average mobility of the electrons. So J equal to sigma E, that equal to rho into P into N1 plus N2 into mu bar into E. So that equal to E N naught mu bar into E, where N naught mu bar is the average mobility, that equal to N1 mu1 plus N2 mu2 by N naught. And the applied field is raised. If you increase the applied field even higher, almost all the electrons in the L valley are transferred to the upper valley and the current density will be given as. So if you further increase the applied field, even at a higher, the almost all the electrons in the L valley are transferred to the U valley. And the current density can be written as J equal to sigma E, that is similar to E N2 mu2 into E, where N2 is the carrier concentration, mu T is the mobility in the upper valley. So mobility in the U valley. So the J versus E, the current versus E curve is obtained to similar to the VI characteristics of the junction diodes for the voltage controlled bulk negative conductance gallium arsenide sample. So the J versus E curve is obtained. Those are similar to VI characteristics of the normal PN junction diodes for the voltage controlled bulk negative conductance gallium arsenide sample, as shown in the figure. So from the figure it is observed that where Jm is the maximum current density, Jm is the maximum current density, and Jv is the valley current density. So Jm is the maximum current density and Jv is the valley current density. Em is the maximum electric field required before the onset of the negative conductance region. And Ea is the maximum electric field. Ea is the maximum electric field for which J equal to sigma E is valid. Eb is the electric field for which J equal to E N2 mu2 into E. So EV is the electric field corresponding to JV. So from the figure, these are the current density versus electric field characteristics. These characteristics are similar to the VI characteristics of the normal PN junction diode. So from this figure, we obtained that negative differential mobility region. So this is the negative resistance mobility region. So here Jm is the maximum current density. So maximum current density is 2 into 10 power 7 centimeters per second, and Jv is the valley current density, that is 1 into 10 power 7 centimeters per second. So Em is the maximum electric field required before the onset of the negative conductance region, and Ea is the maximum electric field for which J equal to sigma E is valid, and Eb is the electric field in the upper valley, that is J equal to E N2 mu2 into E. So where EV is the electric field corresponding to JV. So here mu L equal to Vd by E, mu N equal to dVd by dE. We are differentiating dVd by dE. And mu equal to Vd by E and Vd equal to F into L, where Vd is the electron drift velocity, F is the frequency, L is the device length, J is proportional to terminal current, E is proportional to applied voltage. Hence, this J characteristics represents the VI characteristics of the gun diode. So, the region of the characteristics between EM and EV, where the current density decreases with increasing the electric field, is one of the negative differential resistivity, that is called NDR. So, differentiating J equal to sigma E, E N naught mu bar into E with respect to E, where mu bar is the average mobility. So, by differentiating with respect to E, dJ by D equal to sigma into 1 plus E by sigma into D sigma by DE. So, the condition for negative conductance or resistance is dJ by DE is less than 0 or 1 plus E by sigma into D sigma by DE is less than the 0. That is the condition. So, the JE characteristics represents the VI characteristics of the gun diode. So, the region of the characteristics between EM and EV, where the current density decreases with increasing electric field. Here, the current density will be decreased with increasing the electric field, is one of the negative differential resistivity, that is called NDR. So, differentiating J equal to sigma E. So, that equal to E N naught into mu bar into EV with respect to E, we get dJ by dE equal to sigma into 1 plus E by sigma into d sigma by dE. So the condition for the negative conductance or resistance is dJ by dE is less than 0 or 1 plus E by sigma into d sigma by dE, that is less than 0. Hence, if dou E by dou sigma satisfies the above equation, that is, if differential conductivity is negative, then the slope of the VI characteristics will be negative and the device will present a negative conductance or resistance to the external circuit. So, if dou E by dou sigma satisfy the condition, that is, if differential conductivity is negative, then the slope of the VI characteristics will be also negative and hence the device will present a net negative conductance or resistance to the external circuit. So, it is to be noted here that this intervalley transfer must take place at realistic field levels. So, the threshold field EM should not raise the temperature so high as to cause significant generation of electrons from the valence band by impact ionizations. So, it is to be noted here that this intervalley transfer must take place at realistic field levels. So the threshold field UM should not raise the temperature so high to cause the significant generation of electrons from the valence band by the impact ionization. So thus delta E should be less than EC as in the case of N-type gallium arsenide. So delta equal to 0.36 electron volts. EZ is the energy gap. Energy gap is the 1.43 electron volts. So then domain formation. When a DC bias of value is equal to 1 more than corresponding to a threshold field of about 3.3 kilovolts per centimeter is applied to N-type gallium arsenide sample. So we are applying the DC bias to the N-type gallium arsenide sample with a threshold field of about 3.3 kilovolts. So the charge densities and the electric field within the sample become non-uniform, creating the domains. So due to the non-uniform, which will create the domains, that is electrons in some regions of the sample will be first to experience the intervalley transfer than the rest of the sample. So when the DC bias of the value equal to 1 more than the corresponding to a threshold field, that threshold field is 3.3 kilovolt per centimeter is applied to a N-type gallium arsenide sample, the charge densities and the electric field within the sample become non-uniform. So the charge densities and the electric field will become non-uniform means which creates the domains. That is, electrons in the some regions of the sample will be experience their intervalley transfer. Intervalley transfer means the electrons are transferred from lower value to upper value than the rest of the sample. So the dipole domain formation is observed from the figure. The electric field inside the dipole domain would be greater than the fields on either side of the dipole. So the electric field inside the dipole domain would be greater than the fields on the either side of the dipole. So this is the dipole domain formation. Here, this is the direction of the motion of the electrons. So this is the direction of the motion of the electrons. Here, maximum electric field is applied in this direction. So this one is the cathode end, this one is the anode end. So the layer of excess electrons due to the thermal fluctuations or noise in the current density. So these are the negative, this is the positive here, this is the length. So this one is called as the domain formation. Domain formation. Applied field and the field due to the accumulated charges are both sides present. If the applied field is at a threshold, the field at the anode side of the accumulation charge exceeds the threshold and the electrons in that region or domain move with less mobility mu2 of the U value. Already we know that the mobility in the U value is less compared to the mobility in the L value. So the applied field and due to that applied field, the accumulated charges are both presented. So the accumulated charges positive and negative is present. If applied field is at a threshold field, the field at anode side of the accumulation charges exceeds the threshold and electrons in that region or domain move with a less mobility, that is mu2 of the U value. This creates a slight excess of electrons in that region and a slight deficiency of electron in the region immediately ahead. The region of excess and deficient electrons from a dipole layer. So this creates a slight excess of electrons in that region and slight deficiency of electrons in that region immediately ahead. So the region of excess and deficient electrons from a dipole layer. So as the dipole drifts along, more electrons in the vicinity will transfer to the U valley until the electric field outside the dipole region is depressed below the threshold electric field. So as the dipole drifts along, more of the electrons in the vicinity will transfer to the U valley until the electric field outside the dipole region is depressed below the threshold electric field. So this dipole continues towards the anode until it is collected. So upon the collection, the field in the sample jumps immediately to its original value and the next domain formation begins as soon as the field value exceeds the threshold value, and the process is then repeated cyclically. So this dipole formation or dipole continues towards the anode until it is collected. Upon the collection, the field in the sample jumps immediately to its original value and the next domain formation takes place as soon as the field exceeds the threshold value, and the process is then repeated with cyclically. So the time taken by the dipole domain to travel from cathode to anode. So the time taken by the dipole to travel from cathode to anode is the transit time of the device, that is called transit time of the device. So the fundamental frequency in megahertz is given by F equal to Vd by L. where Vd is the drift velocity, that is 105 meters per second usually. So L is the device length, that is in micrometers. So the domain formation usually starts near cathode, and because of low field and high carrier charge density in the region, the width of the domain is inversely proportional to the doping level in the sample. So the domain formation usually starts near the cathode, and because of low field and high charge carrier density in that region, the width of the domain is inversely proportional to the doping level in the sample. So depending on the material parameters and operating conditions, a gun effect oscillator can be made to oscillate in any one of the four frequency modes. So here the four frequency modes are available depending on the material parameters and operating conditions. First one is the domain mode. So domain mode means dipole transit time or traveling domain mode. So transit time means the domain is the dipole is traveling from cathode to anode. That time is known as the transit time. So the domain mode, the dipole transit time or traveling domain mode. So second one is the delayed or inhibited domain mode, and third one is the quenched domain mode, and fourth one is the limited space charge accumulated mode, which is called LSA mode. So these are depending on the material parameters and operating conditions. The gun effect oscillators can be made to oscillate in any one of the four frequency modes. So there are four frequency modes are available. These are, first one is the domain mode, second one is the delayed or inhibited domain mode, third one is the quenched domain mode, and fourth one is the limited space charge accumulator LSA mode. So this one is the construction of the gun diode. So this is the construction diagram of the gun diode. Here we observe that gold wire bounded to a flange, and this one is the ceramic spacer. This one is the epitaxial gallium arsenide device with SN dot contact. SN dot contacts. These are the gold plated molybdenum stub. So this one is the top cap. This is the construction of the gun diode. So the typical characteristics of the gun diode is it typically uses a 10 to 12 volts supply with a typical bias current of 2 250 milliamperes, giving a continuous wave power of 25 milliwatts in the X band. So the typical characteristics of the gun diode is it is typically uses the 10 to 12 volts power supply with a typical bias current is 250 milliamperes, which gives a continuous wave power of 25 milliwatts in the X band. So the continuous wave power, that is 25 milliwatts to 250 milliwatts X band, the frequency range is 5 to 15 gigahertz. 100 milliwatts at 18 to 26.5 gigahertz and 40 milliwatts at 26.5 to 40 gigahertz. The pulsed power is 5 watts. The frequency range is 5 to 12 gigahertz. The efficiency is 2% to 12% at 1.5 watts continuous wave to 5 milliwatts continuous wave power. Then applications of the gun diode. So gun diodes are used in the radar transmitters, that means police radar, CW, Doppler radar. So applications of gun diode, the first application is the radar transmitter. So gun diodes are used in the radar transmitter, that is police radar and CW Doppler radar. So pulsed gun diode oscillators used in a transponders for air traffic. So ATC control purpose also we are using the gun diodes and in industry telemetry systems. So broadband linear amplifier replacing the TWTS. So fast combinational and sequential logic circuits, low and medium power oscillators in the microwave receivers, and as uses as pump sources in the parametric amplifiers. So these are the applications of the gun diode. First one, the gun diodes are used in the radar transmitters. Second one, pulsed gun diode oscillators. Third one is the broadband linear amplifier. Fourth one, fast combinational and sequential logical circuits. Low and medium power oscillators in the microwave receivers. These are the applications of the gun diode. These are the references for semiconductor devices. Donald A. Neem, SMG, and Kulkarni, Microwave and Radar Engineering. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.